I'm Professor Brad Fulton, and welcome to my Stats podcast. This is an edited audio recording of my course. Each lecture is its own episode, and there's a total of 24 lectures. This course provides an introduction to the quantitative methods social scientists and data analysts use to collect and evaluate empirical data about society. Through this course, you will learn to gather, describe, and analyze data with an emphasis on the application and interpretation of these methods. This course will also help you to be a more informed and critical reader of academic research, public opinion polling, and advertisement claims that present statistical evidence. Although some of the current events I reference might be dated, the content is timeless. I hope you enjoy this lecture, and if you have any questions, you can email me at bradrfulton@gmail.com. Hi, my name is Professor Fulton. If you like this podcast, you'll love the book I use for the course. It's titled Statistics, Unlocking the Power of Data. This book uses a highly intuitive approach to help students visualize statistical concepts, which accelerates understanding. I've reviewed dozens of textbooks, and Unlocking the Power of Data is hands down the best one out there, mainly because of its unique intuitive approach and straightforward explanations. You can find a link to the textbook in the show notes, and if you use the promo code BLOCK5, you'll get a 10% discount. So the question was, how is a person's happiness related to their frequency of attending religious services? And it's very similar to some of the research questions that you guys are working on. The research question is, you pick a dependent variable, an outcome that you're interested in, whether it's happiness or an attitude about homosexuality or government intervention. So each of you have sort of picked an outcome that you're interested in, and then you want to know what characteristics or what things would be associated with that outcome. An example, the outcome, let's say, that we're interested in for this is happiness, and one of the things we want to look at is how religious attendance is associated with happiness or not. An important thing that you'll need to do, especially as you begin to pick your variables, is you need to start by just understanding your variable. I'll pick happy as one. So you put happy up in this box, and then you hit view. It's a categorical variable, and the question is, taken all together, how would you say things are these days? Would you say that you are very happy, pretty happy, or not too happy? That's a categorical variable with three primary categories: very happy, pretty happy, and not too happy. But this is also known as an ordered categorical variable because each of the responses has a value associated with it, and as you increase the value, you're moving along a scale. With this, it's ordered from very happy to not too happy. Whereas, like, if you looked at the race variable, it would have black, white, other, and each of them would have a value associated with it, but it isn't an ordered thing. There isn't a hierarchy numerically to race. But with happy, it is ordered, and so in this way you can treat it as a quantitative variable. It's just like income. At the low end of the spectrum is low income, and then as you move up the scale, you have high income. So the other important thing to notice, and this will be with every variable, is you have to see how it's ordered. So actually, as you go up in value, your happiness score is actually going down. The way it's set up is not particularly helpful because you're thinking, oh, if I have a higher happiness score, I'm probably happier. But that's why you really need to look at how the variable is coded. In whatever variable you're working with, you'll need to do this. And that'll probably be one of the next assignments, is picking your variables and then interrogating them to make sure that they're measuring what you think they're measuring. I think one person wanted to look at people's attitudes towards homosexual marriage. And so there's a variable called homosex, and they were going to use that variable. But the problem is that variable just measures your attitude about homosexual behavior. And it doesn't say anything about homosexual marriage. So you wouldn't be able to use that variable to make inferences about attitudes about same-sex marriage. I'm going to make sure that what you're claiming to make claims about, that you actually have variables to measure that. The next step in that process is going to be, what variables are you going to use, and then describe the variable in multiple ways. And one of it would be here's the categories, here's how it's ordered, and here's the mean. So even with this one, even though it's categorical, you can actually calculate the mean. So if we type in happy and we run the table, this is the proportion of respondents that were happy. 33% said very happy, 55% said pretty happy, and 11% said not too happy. But then if you go down, this tells you right down here, the mean is 1.78. And so what that's saying is the mean happiness scale for people in the US is between very happy and pretty happy. So you might think with a categorical variable, what does the mean tell you? Well, if it's an ordered categorical variable, it'll let you know that the center point of the level of happiness for the people in the US. And same with standard deviation and variance and stuff like that. So actually, if you're going to use this as a quantitative variable, you would have all the information you need to enter into the formulas. You would have standard deviation, and you can use all that. It started off as a categorical variable, but because it's ordered, I can treat it like a quantitative variable. And not all categorical variables are ordered. So we want to look at the correlation between happy and attend. I have so many windows open, but okay, this one will work. This pops up, it gives you the correlation between happy and attend. Negative 0.14 is our point estimate. What does that mean? How would you interpret that point estimate? Okay, there's a negative correlation between happiness and attendance. So this is taking the happy variable and it's saying as you increase values on the happy scale, you're going to see a decrease in religious attendance. So Brittany.
The happy scale is like backwards. So
yeah.
It's actually a positive correlation because it's like the happy scale gets larger. It means
Yep.
you're more unhappy.
Yep. So that's exactly right. But you would never know that. The naming of this variable is not helpful. But because it's ordered such that as you increase values on the happy scale, what that's meaning is you're becoming less happy. Just because of the way that they've coded the variable. It's fine to make this mistake, and it should be called unhappy. As religious attendance goes down, you become more unhappy. It's more important that when you are looking at your variables, that you know what's going on and what it's measuring. And there's ways to recode the variables or change them if you want to just look at specific things. So at the end of the day, GSS and all other programs will provide you the standard error, but I will expect you to know how to calculate the standard error. But at least in this situation, you could keep trying to calculate the standard error until you matched or got close to what was on GSS. Based on this, is our p-value then for the correlation between happiness and religious attendance, is it then 0.004? It's not. Why?
Let's just use standard errors.
Good. A common error is to look at this value and it sort of has that p-value look to it, but it's not the p-value. All that tells you is how much error there is in your point estimate. How much variation would there be if you did a new sample and took the sample statistic of the correlation between happy and attend. It tells you how much variation there would be. And you use that value then to calculate your t-statistic and get your p-value. That gives a quick overview of part 2, and then we'll move on to the main lecture. So the past 4 lectures was looking at inference for categorical and quantitative variables, and I'll say is the simplest level scenarios. And so these subsequent lectures are going to be when you have more complex scenarios, and how do you approach them when you have just more complex variables. What we're going to look at today is what's called chi-square test. The chi-square test is designed for when you have multiple categories. So far we've learned how to do inference for categorical variables that only have 2 categories. Like whether you're aware of it or not, we've always limited it to male or female or black and white. And it's always been situations where the categorical variable only has 2 categories. But in reality, we're going to find categorical variables that have multiple categories. We need to know how to do inference for categorical variables that have multiple categories. Today we'll learn how to do hypothesis tests for categorical variables that have multiple categories. So here's a simple, familiar example of a categorical variable with 3 categories. We have rock, paper, scissors. And I'm bummed that Tim's not here because we can't have a real competition to go head to head. We'll do it anyway. I want you to pair up and do one round of rock, scissors, paper.
Rock, paper, scissors.
We have a sample of 6, and so I want to know how many people threw a rock. Brittany and Rachel. How many people threw a paper? And scissor. We could do this multiple times. If you had a larger classroom, you could do it with everyone, and you would get a distribution of values. And what we have here is a categorical variable, and because it's categorical, we have proportions. Here's the distribution of proportions. That's what we're going to be working with.
0.17.
0.17. So which option did you throw? We did that. Now, here's the question. Can we use statistics to help us win at Rochambeau? Is there a way that we could use statistics?
Yes.
Technically,
my
yes?
guess is there's not going to be a statistical significance between the 3, but...
Okay, so if you would test for what?
Which one's more commonly used?
You could say, is any one more commonly used, and then which one of those? So yeah. So we could take a sample and test whether each of these options are equally likely to be thrown. And if they're equally likely to be thrown, then it's just random chance. But if there is some sort of bias in what people throw, then you could use statistics to beat your friends. So we did this with a larger sample of 98 people, and this was the distribution of what people threw. How would we test whether each of these options are equally likely to be thrown? So that's our challenge. Here's the distribution, and we could then look at the actual proportions. If there was no inborn bias towards what people throw, then how likely would this occur by random chance? And so it's a similar type of question, like if all the proportions are equal, then how likely could we get that just by random chance? So we do hypothesis testing. We start by stating the hypothesis, and then we calculate a test statistic based on our sample data, then create a distribution of this test statistic as it would be observed if the null hypothesis was true. We had 98 samples and you have 3 proportions. And so your test statistic is that combination of 3 proportions. Because we're using a more complex variable, your test statistic becomes more complex. It isn't just one value, but it's a combination of values. And then you measure how extreme your observed test statistic is when compared to the distribution generated under the condition that the null hypothesis is true. The way that you would set up a hypothesis test for a chi-square test would be let pi denote the proportion of the ith category. Now whenever there's i's and iths in there, it gets confusing. The way to think about it is what are the categories that I'm actually measuring? In this case, it's rock, paper, scissor. So P1 would be rock, P2 would be paper, and P3 would be scissors. That's all it's saying with that fancy notation. So then the null hypothesis, if there is no difference, is no effect, would be that every PI has the same value. Every proportion would be the same. And so every PI in this scenario would equal 1/3 because you have 3 categories. If each one is equally likely to be thrown, then the population proportion would be 1/3. So then our alternative hypothesis is that at least one PI differs from the others. You make it a very generous alternative hypothesis. All you want to know is, does any of the 1 PIs differ from the others? The null hypothesis is always a very tight, specific thing, and then the alternative hypothesis is like, is there something else going on? Because that's ultimately what we're testing. We're seeing, whether we reject or accept the null hypothesis. The alternative written out would be at least one PI doesn't equal 1/3. So we don't have to say what direction or which PI, just one of them doesn't equal 1/3. And so just like we did in the past, we have a standardized test statistic. So we can't use the familiar formula that says the sample statistic minus the null value over the standard error. That's what we've been using as the standardized test statistic. But the reason why we can no longer use this simplified formula is because one is that we have more than one sample statistic. We're working with 3 proportions now because we have multiple categories. We have more than one sample statistic. It's like, what would you put in there? And then also we have more than one null value. So both the sample statistic and the null value are more complex than in the stuff that we've been doing. An important step in this process is distinguishing between these two concepts. The first is the observed counts, and they are the actual counts observed in the sample. With the one where we did 98 people, the observed counts for rock, the number of people who threw rocks was 34, the number of people who threw paper was 24, and the number of people who threw scissors was 40. So you had observed counts, and now you have expected counts. And the expected counts are the counts if the null hypothesis was true. If we have 98, the expected counts would be 33, 33, and 33. That's not right though, because we did 98 throws, so I'm going to have to figure that out. But it's close enough to where I think you guys get the point. The expected counts is if there was no internal bias of what people would throw, the expected counts would be equal across the board and be divided by 3.
Do you round those down or up?
With these right here,
Yeah.
I need to figure that out. I don't know why. To make the example simple, I should have said 99, so I need to look at that. But in the end, yes, you could just round up, or you could even keep the fractions in there. But just to sort of maintain simplicity, it's basically each of these values is going to be a third of your sample. And maybe that's what was done, is that it was rounded up. So for each cell, the expected count is the sample size n times the null proportion. So it'd be 98 times pi, 1/3, and then it rounds up. So that's how you calculate the expected count.
The last thing it stays at like 1/3.
No, for that scenario, it's 1/3 because you have 3 categories, and our null
by categories.
It goes by categories and what your null hypothesis says. So in our null hypothesis, we said that every category is equally likely to occur. But you'll see other examples where our null hypothesis says something different, and so you need to look at whatever the null hypothesis is. That's what determines your expected counts. The number of counts that you would expect if the null hypothesis was true. We've learned the Z statistic, the T statistic, and now here's the chi-square statistic. And if you're building your cheat sheet that maps out all of these and when you use them. In general, a test statistic is one number computed from the sample data which we can use to assess the null hypothesis. So test statistic is the general word, and then we have specific test statistics. For multiple categories, we use what's called the chi-square statistic, and it's a test statistic for categorical variables. And the way you calculate it is, this is the summation symbol, and you do observed counts minus expected counts squared divided by expected counts. You would do this, you would sum it up for each category. So you would take your first category, rock, and you would do observed counts minus expected counts squared divided by expected counts. And then you do the same thing for paper, observed counts minus expected counts squared divided by expected counts. And so on. The chi-square statistic that we get for this example is 3.97. That's very similar to when we would get a Z statistic or a T statistic, a standardized version of our test statistic. Let's say our observed counts were all 33 as well, like exactly the same as the expected counts. You'd have 33 minus 33 equals 0, equals 0, equals 0, and our test statistic would be 0. It would basically say that our observed counts exactly matched what our expected counts were, and so the null hypothesis that there's no difference in what's going to be thrown, we would say, okay, we can't reject that because that's what we would expect if the null hypothesis was true. The more our observed counts deviate from our expected counts, the larger chi-square will be. If one of these categories, even so like scissors, the observed counts deviates a lot from the expected counts. As the observed counts deviate more and more, this is going to push up the chi-square value. The more our observed counts deviate from what our expected is, then that's telling us that there's some effect, there's something going on. Chi-square score of 3.97 measures how close the observed counts from the sample of 98 rounds of Rochambeau are to the expected counts under a null hypothesis of equal proportions. We have two scenarios. We have our observed counts, and then we have what would be expected if the null hypothesis was true, and we want to see how closely matched are these counts. And now that we've calculated the test statistic, chi-square equals 3.97 for our sample, we need to determine the distribution of chi-square statistics. So following on what McKay said, like eventually we'll go to stat key, but we need to know what is the distribution of chi-square statistics. So what's the distribution of z statistics? If we gather multiple values for the z statistic, how would they be distributed? What would be the shape of that distribution? So this is the standard normal, okay?
So it's shaped the same way, but the exact shape of it varies based on your sample size.
Okay, so T is very similar, and that's how T statistics are distributed. And as degrees of freedom, as that goes up, then it is almost exactly the same as the standard normal. But on stat key, if you're looking at T statistics, if you have a T statistic, you're going to go to the T distribution. And if you have a Z statistic, you're going to go to the normal distribution. Now we have a new test statistic called the chi-squared statistic. And what we need to find out is if we did that experiment 1,000 times and we came up with 1,000 chi-square statistics, what would be the distribution of chi-square statistics?
Right skewed.
Right skewed. Okay, why do you think it's going to be right skewed?
That's what the pictures in the book show.
Ah, interesting. So when the null hypothesis is true, all of the expected counts are going to equal each other. The distribution, if we ran the test 1,000 times where the null hypothesis is true, and remember with this line here, if our observed counts exactly matches our expected counts, then chi-square equals 0. So for each time we run the experiment, we're going to calculate the chi-square statistic. The chi-square statistic is going to vary each time, but a value that's going to come up a lot is going to be 0. Because if we're saying what is the chi-square statistic going to be when the null is true, when the null is true, chi-square is going to be approaching 0. And so that's going to influence the distribution of chi-square statistics. We're going to look at what the distribution is, and once we find it, then we need to assess the location of our observed chi-square statistic on the distribution of chi-square statistics under the condition that the null hypothesis is true. So just like with Z and T, we find out what the distribution is, and then we take our observed sample statistic and put it and see where it fits on the distribution. So, and that's then how we calculate p-value. So we're going to do the same thing once we figure out how the chi-square statistic is distributed. There's two ways to obtain the distribution of chi-square statistics under the condition that the null hypothesis is true. The two are using a simulation procedure or using distributional theory. And so the simulation procedure is what we've done with randomization, where we reallocate the options such that we would see what would happen if the null hypothesis was true. And distributional theory is if we can know the distribution of the chi-square statistic, then we can use that information to estimate what it would look like. So with simulation, the way that you approach it is very similar to how we did the other simulations. It's what would a distribution of chi-square test statistics look like if people were equally likely to choose rock, paper, or scissors. A mechanical way that you can do it is take 3 pieces of paper and label one rock, paper, and then scissor, and then crumple them up so that they're indistinguishable, and then you just pick one of them. And then you record what you pick, put it as a count of either rock, paper, or scissor, and then you'd replace the piece of paper and repeat the process 97 times so you would get to your sample size of 98. So this is mechanically to do the simulation. You could also do it with a computer, but you're basically trying to get multiple chi-square statistics. And so then you would have your next sample of 98, and you would calculate the chi-square statistic for that sample. So in our observed sample, the chi-square statistic was 3.97, and then what we're wanting to know is what is the chi-square statistic if the null hypothesis is true? And by having the 3 pieces of paper, we've sort of eliminated any type of bias or whatever. Each of them has a 33% chance of being picked. We calculate the chi-statistic for this sample where the null hypothesis is true, and then repeat this process 10,000 times to obtain a distribution of chi-square statistics. What we originally had was our 3.97, which was our observed test statistic. But like all test statistics, they vary. They're going to vary from sample to sample, and we want to know how much they vary from sample to sample. And because we're doing a hypothesis test, we want to know what the variation would be if the null hypothesis was true. What we would ultimately get, though, with step 5, is a distribution of values, a distribution of chi-square statistics where the null hypothesis is true. And then we would assess the probability of getting your observed test statistic by random chance if the null hypothesis was true. Through computer simulation, we simulated 10,000, like doing it like the paper example where you just pick up one and calculate it. And so here's the distribution of values. So each time you do it, you're going to get a slightly different chi-square statistic. You're going to get a different value because it's going to be at random. And so the counts, they aren't going to all be 33, 33, 33. It's going to vary slightly because you're just doing it at random. But remember how I said, in general, if the null is true, which is what we're simulating, there's going to be a lot of values hovering around 0 because when you do the observed counts minus the expected counts, and if those are equal, they're all going to zero each other out. And so you're going to get a lot of values clustered around 0. But then if there's any variation from the observed and the expected, it's going to increase the chi-square score. If you did run the simulation, this is what the distribution of chi-square statistics would look like. And so this is what's known as the chi-square distribution. This is the z distribution, this is the t distribution, and so this is the chi-square distribution. Then we look at our observed chi-square statistic, and it's 3.97. And then you calculate the p-value by saying what are the proportion of test statistics that are as extreme as our observed test statistic. So it's the same process, but one of the challenging parts in this is figuring out what is the distribution of chi-square statistics. But once you know the distribution, then you can see where your test statistic fits on the distribution. In the same way, the p-value. So the probability of getting a test statistic as extreme as 3.97 when the null hypothesis is true is 14%. So in this example, what would be our formal decision with regard to our null hypothesis? Our null hypothesis says each option is equally likely to be thrown, and our alternative hypothesis is like, no, one option is more likely to be thrown than another. In a world where each of them are equally likely to be thrown, there's a 14% chance that we would get this type of outcome where you have 24 rocks, 20 papers, and 40 scissors or whatever. Like, there's a decent chance that you would get that type of outcome even if all ones are equally likely to be thrown. We shouldn't be surprised when we saw the proportions that we saw. Chi-square distributions, if each of the expected counts is at least 5, so each of the cells is at least 5, and if the null hypothesis is true, then the chi-square statistic follows a chi-square distribution with degrees of freedom equal to the number of categories minus 1. So just like the t-distribution has degrees of freedom and it varies based on variables you're looking at, so does the chi-square distribution. Its degrees of freedom is the number of categories. So as you increase the number of categories, you increase the degrees of freedom. In this case, we have rock, paper, scissors. Degrees of freedom would be 3 categories minus 1 equals 2. So we go to stat key, and then we want to know where our test statistic, our chi-square statistic, fits on the chi-square distribution. And then our degrees of freedom, 2. So this is our chi-square distribution, and we want to know the proportion of values that are as extreme as our test statistic. So what would be the next step? Right tail. Edit parameters. Okay, let's see what that does. that says, please select degrees of freedom. We did that, so that's 2. That's good. Rachel?
Switch the bottom value
to 3.97. This tells us the proportion of test statistics that are as extreme as our observed test statistic when the null hypothesis is true. And so the p-value is 0.137. Based on this, we can't reject the null hypothesis because there's a 14% chance that we would get this outcome if the null hypothesis was true. It's the same procedures that we've done, but it's now looking at a different type of distribution, a different type of test statistic. This is what the chi-square distribution looks like. And so you can see as the degrees of freedom change, the distribution changes slightly. But fortunately, you'll be able to figure out what the degrees of freedom is, and in StatKey, you can plug in the degrees of freedom, and it'll give you the distribution that you'll be working with. But in general, it follows a very similar pattern. An important thing to note is that because chi-square is always positive, it's always going to be a positive number. So if you ever get a negative number, you know that you've made a mistake.
There's always right tail.
Yes, exactly. So then you don't have to make a decision of like right tail, left tail, two tail. With chi-square, you're always saying what proportion of values are as large as our test statistic. The way that this is looked at is in the terms of goodness of fit. How well does the distribution of proportions in your sample fit the distribution of proportions expected under the condition that the null hypothesis is true? More formal way of stating what we're testing. If it fits well, you cannot reject the null hypothesis. If it doesn't fit well, you can reject the null. So you want to know how close is the breakdown of observed proportions to your expected proportions. And we use the chi-square test to assess that. A chi-square test for goodness of fit tests whether the breakdown of proportions for a categorical variable is the same as some null hypothesized breakdown. This is just to answer Tim's question. The null hypothesized proportions for each category do not have to be the same. So you could have a null hypothesis where it's a different breakdown of proportions. A chi-square goodness of fit test, that's what you'll see in the book, and that's sort of how it's presented. Is basically another way of saying a hypothesis test for categorical variables with multiple categories. The way you do it is you state the null hypothesized proportions for each category, and then the alternative hypothesis is that at least one of the proportions differs from what's specified in the null. The null is the key one. You want to have precise claims that you're making. The alternative is to deviate from that in any way. Then you calculate the expected counts for each cell, and that's where we do the sample size times the expected proportion, and then make sure that they're all greater than 5. That's just so that the conditions will be met for using the chi-square distribution. And then you calculate the chi-square statistic, which is the formula that we had looked at, and then once you get the chi-square statistic, you're going to obtain the p-value as the proportion of values beyond the chi-square statistic for a chi-square distribution with specified degrees of freedom. The final thing is to interpret the p-value in context. I will say a lot of you have been giving me the p-value and even correctly saying reject the null or don't reject the null, but I want more. I want to know how do you interpret the results. Let's see, we're going to look at 2 categorical variables. So now you take it to the next step if you're looking at 2 categorical variables. How does chi-square test work with that? And fortunately, the statistics behind the chi-square test extend to 2 categorical variables. So we did with Rochambeau was 1 categorical variable, and now we're going to look at 2 categorical variables. So for 1 categorical variable, it's called a goodness of fit test. And then for 2 categorical variables, it's a chi-square test for association. Sometimes it's called a chi-square test for independence, but a test for an association between 2 categorical variables. It could be gender and race, it could be gender and happiness, or whatever your 2 categorical variables, and if you want to see if there's a relationship between the 2. It's the same formula, observed counts minus expected counts squared over expected counts, so you're going to use the same process. Now this is where it differs because you're working with 2 variables. So degrees of freedom is going to be r minus 1 times c minus 1. R is the number of rows, which is basically the number of categories for variable A, and then C is the number of columns, the number of categories for variable B. And then the expected count for each cell is the row total times the column total divided by sample size. I'll give you a specific example so you can see what this actually looks like. The reason for doing this when you're doing a hypothesis test is that it maintains the row and column totals but randomly redistributes the counts as if there was no association between the variables. So the chi-square test for association, the formal process for doing that, state the hypothesis, and the null hypothesis is that the two variables are not associated. So this is kind of similar to what we learned with correlation. Either they're associated or not associated, and the alternative hypothesis is that the two variables are associated. There is a relationship between gender and happiness. And then the second step would be calculate the expected counts for each cell, make sure they're all greater than 5 to meet the conditions, and then you're going to calculate the chi-square statistic, doing it the same way that we did with Rochambeau. And then once you get the chi-square statistic, you're going to obtain the p-value as the area under the tail beyond chi-square statistic for a chi-square distribution with the degrees of freedom. And then notice the degrees of freedom is different because you're using two categorical variables. And then interpret the p-value in context. For any of you who read the article on black churches and HIV/AIDS, there's an analysis where we looked at two categorical variables, or multiple pairs of categorical variables. And one of them was, is there association between a congregation collaborating with outside organizations and having an HIV/AIDS program? And we're going to use the most simple example where you have two categorical variables with two options. And so the question for this variable was, does your congregation collaborate with outside organizations? And it was a yes or no. And then the second question was, does your congregation have an HIV/AIDS program? And it was yes or no. So those are two categorical variables. So here's the table. So when I was talking about rows and columns, what you would do is put one variable along the top, which is, do you collaborate or not collaborate? And then the other variable is going to be the side, and it's, do you have an AIDS program or you don't have an AIDS program? And so then this is our observed sample. So we have total number of 203 congregations. 32 congregations have an AIDS program and collaborate with outside organizations. 9 have an AIDS program but do not collaborate with outside organizations, and so on. So you can begin to see this is the breakdown of the proportions. So we state the hypothesis. The null hypothesis is there is no association between the two variables. So this breakdown that we're observing, we're kind of saying there's a decent chance that that could have just happened randomly if there was no association. And the alternative hypothesis is, no, there is an association between the two variables. Like, there's a tendency that if a church collaborates with outside organizations, they're going to be more likely to have an AIDS program. Like, we think there's some sort of association. It doesn't necessarily cause them to have an AIDS program, but we know that doing both of these things are somehow related to each other. It isn't just random chance that they have an AIDS program and collaborate. So then we calculate the expected counts for each cell. So this is our observed counts, and in order to calculate the chi-square statistic, we need to know the expected counts. The way you do that is the row total times the column total over the sample size. You have row total 39 times column total, which is 108, divided by sample size. That should say 32. For cell 1, you would do it, then you do that for each cell, and then you would come up with, here's the yellow is our observed counts, and then the white is our expected counts. And we need those values then to calculate the chi-square statistic, which is this, where we're using the observed counts minus expected counts over expected counts. And if you map that out, you end up with a chi-square statistic. So that's our test statistic for a test for association. And so then what are we going to do with that value? Is that our answer? You do p-value. Okay, so let's see. 13.9, let's say. So what it's saying is we reject the null that says there's no association and say, yes, there is some association between collaborating and having an AIDS program. Good. We actually got through all of it. The focus of today was the chi-square distribution and looking at categorical variables with multiple categories. So one variable or also the association between two variables.